Hello everyone. Hello everyone. This is Vijitha, Assistant Professor from CSC Department from TKREC College. Here we are here to discuss about an AVL trees. AVL trees are before going to the AVL trees. What is a tree? First of all, we'll check it out. What is a tree? Why, first of all, these trees are used? These trees are used to communicate from one node to the another node. Whatever the data is there, that should be transferred from one node to the another node. If it is nearby, is okay, but if it is in a very long distance, we have to concentrate on the particular paths. So here, first of all, we have to give the structure for particular nodes from where to where the data is starting and where it is ending. Means first one root node is selected, then that the other nodes will be attached to that particular root nodes as a child nodes. And coming towards a tree structure is nothing but a hierarchical structure which is used to represent and organize the data, whatever the data we people are putting in a format in such a way that to navigate and search that particular path or the data. And it is also called, it is a collection of nodes which are connected by edges and has a hierarchical relationship between the nodes. Here we have come across through the edges. These edges are nothing but the link between one node to the another node. This is a hierarchical structure of a tree. Here we can see the root node along with the child nodes, that child nodes again acting as a parent node towards another child. So here these nodes we can calculate in the form of a decrease, means that can be considered as a levels. The root node level will be considered as a 1, sorry 0, and the next child of the particular node will be considered as a level 1, then their child will be considered as a level 2, in such a way that how many nodes are attached, those are all will be considered in the level wise. And coming towards these parent nodes, wherever the nodes have the children, means the node which contains the child nodes, that particular node will be acting as a parent, and the nodes which don't have any nodes further will be acting as a child nodes to the parent one. And the nodes with zero elements, zero nodes are called as a leaf nodes. And the parent node which have the one or more children are called as a sibling nodes. So these are the few basic terminologies to know the tree structure. So why we people are discussing about a tree? Because to as the AVL tree, to discuss the AVL tree, first of all we need to know the binary. We need to know the tree, and then we people will be we need to have the knowledge on a binary tree. We have checked the tree, that is a hierarchical structure, and how the nodes will be attaching to the each node randomly. Now coming towards the binary tree. What is a binary tree? These binary tree can be, in this binary tree, a nodes can be arranged in any fashion in such a way that one root node with a child nodes, that child nodes may act as a parent nodes. And here, if you observed from the previous one and the next this binary tree, here we have attached the number of trees wherever we want. We didn't follow any sequence of arranging that particular nodes. We are attaching either left to right or left and right childs, or else in the one sequence only. Clear, everyone? So depending on the user requirements, the new nodes can be attached to the left or right child of the desired node. Means whoever, if the user want to attach the node at a right side, leaving the left side empty, he can attach over there. But it is not called as a perfect tree. It is only called as a binary tree. Either one, zeros and ones it will be calculated. Now see, for finding any node is a long procedure. For the user has to search the entire tree is a very big disadvantage for a binary tree. Means if I need to check the node 7, if I want to search the node 7, Then what procedure I need to follow in the binary search? I need to follow the level wise, all the nodes I need to check. Just like I have to check within a root one, node one, and then I'll be going for the second and third, again 4, 5, 6, and then I'll be coming towards the seventh one, not directly towards the seventh one. This is a drawback. Wherever if you want to check that particular node in the tree, the whole tree will be searched. This is the drawback of a binary search. Next, coming towards a binary search tree. This algorithm, this tree will help in searching the particular element very fast. Means it is designed in such a way that the data, whatever you are attaching, that will be arranged in a systematic order. Just like whatever the data you people are taking, that particular nodes will be arranged in such a way that the left node should be less than right node, root node, and the root node should be less than the right node. Means whatever the root node you are taking, that particular root node value should be greater than the left child nodes. And coming towards right nodes, the root node value should be less than the right side. Okay, clear? I'll tell you. The right side nodes should be greater always for the BST. Once again, I repeat the statement. Here, the root node values, whatever the root node value is there, that should be greater than for the left child's, and the root node value should be less than for the right child. Here we'll see one example. I have taken some elements and I have taken the 40 as a root node over here. Here, less than 40 values I have attached at the left side, and greater than 40 values I have attached at the right side. See, 30 is less than 40, so I have selected as a left child. 50 is greater than 40, I have selected as a right child over here. Now, in the same fashion, 25 is less than 30, I have attached towards on the left of that particular parent, and 35 is greater than 30, the parent child, parent node, then I have attached towards on the right side. When coming towards a 50, 45 is a lesser than parent 50. So I have attached towards on the left, and 60 is greater than the parent 50. I have attached towards on the right side. Okay, in this way, if you arrange the nodes in a systematic order, there is an easy way of searching a particular element in this particular binary search. Example, if I want to search 45 or else 60, okay, then I can check, I can compare the required node with a root node. For example, 45 if people are considering, then I'll compare the root node 40 and the 45. As 45 is greater than the root node 40, then I'll be directly checking the elements at the right side. I'll won't consider the left side. I'll be ignoring the left side elements and directly considering the right side elements. Again, in the second step, again I'll be checking the same comparison with a parent node 50. Here in the parent node, I'll compare 45 and 50. Here as 45 is less than 50, then I'll go towards the left side. So in this way, the searching of elements is very easy in binary search tree. For example, if in case of 35, if we have a 55, the 55 node, then is it called as a BST? No, this is not called as a BST. It's a non-binary search tree, as the highest value of the node, leaf node, is more than the root node. As 40 is less than 55, then this is not considered as a binary search tree. The overall statement for a binary search tree is always the left child should be less than the root node, and root node should be less than the right sub child or the subtree. Next, this rule is applied recursively to the left and right subtrees. It will be acting as a recursion fashion. Now, why we have come across the tree, binary tree and binary search? Now here we'll check it out. As the AVL tree is a self-balancing binary search tree, to know that particular tree details, we have come across the binary tree and binary search tree, right? Now, we'll check it out what the exact concept of an AVL tree. Here it is a self-balanced binary search tree in which each node maintains the extra information called as a balanced factor. Means whatever the trees you people are generating over here, these nodes should have one balanced factor. Okay, that balanced factor should range in between -1, 0, and 1 only, not more than that. If we get more than that particular value, then that is not called as an AVL tree. Means the AVL tree will be always calculating the height of the balanced tree. Means the degree levels what we have seen in the first tree. In the first tree, the levels, these particular levels will be calculating the balance factor. Clear? Now, the tree can be made balanced of the recovering any node that can be done with the help of a big O of log n. Log n times means the time complexity here we will be coming across a big O of log n, where n will be acting as a number of nodes. Clear. So these AVL tree was named after the inventor George Elson Welsky and Landis in 1962 to balance the binary structure of that particular height of subtrees. Clear. This is named after the scientist, the inventor name AVL tree. Okay. Now we'll go further. In this, as the binary search tree has the disadvantage of uncontrolled in generating the heights, to control that particular heights, we people will be introducing the AVLs. Means here we can attach any number of nodes based on the concept of a binary search tree. Means the height may be generated to any extent. Because of that extension, we don't have any control on the heights. Okay, to have the control on the heights, we we will come across the AVL tree. To overcome this height balancing problem, the AVL trees are introduced as those trees are height balanced. How it will be height balanced, we'll check it out. Okay. Now, coming towards the definition of that. Definition of an AVL tree is designed in such a way that an empty tree is height balanced if T is a non-empty binary tree. Means the T is considered as a binary tree with a left tree and then a right tree. Okay. Means these are the TL and TR will be acting as a left subtrees and then a right subtrees, the children of the tree. And here how the balance will be calculated. As TL and TR are the heights of balanced trees. Now coming towards the particular heights. Left height, left side height should subtracted from right side height. And that should be less than or equal to 1. Okay, clear? Just now we have seen in the definition that should range the balance factor from -1, 0, and 1. In the same fashion, the tree should contain left child and right child, and there that particular child's heights will be calculated by subtracting from left minus right values. When we calculate the particular subtracting values, that should be range from -1, 0, and 1. That is what the concept we have seen over here. The idea of balancing tree is obtained by calculating the balance factor. Okay. Now, coming towards what is a balance factor? Here, coming towards a balance factor, it is nothing but a node in binary tree which will be defined as height of left subtree should be subtracted from height of right subtree. Okay, see, this is the balance factor formula. Balance factor of a node K will be acting as a node should be equal to the height of left subtree minus height of right subtree, where a tree is said to be balanced if that particular balance factor ranges from that particular range value -1, 0, and 1. Then how we can calculate this minus 1, 0, 1? How we can label it? Means if left subtree is one level higher than right one level higher than right one, then that will be called as a 1. If left and right subtrees are equal, then that will be called as a 0. Balance factor will be called as a 0. If left subtree is one level lesser, means lower than the right one, then that will be called as a minus 1. Clear? Means it is subtracting. If you don't have the child at left side and if you have the child at right side, then that will be treated as a minus 1. If both have the child within a 0 elements, then sorry, if both, the node don't have the child, then those will be called as a 0. And if the node has a left child and if it is not having a right child, then that is called as a 1. Hope this is clear. Now we'll check it out. The AVL balance factor tree structure. Here, this is the tree structure for an AVL tree. I have taken some notes and I have designed the tree structure. Whether it is balanced or not, we'll check it out now. Now, see 100 as an two childs. So both left and right is there. Okay, not an issue. Then again the 50 has an two childs, 150 has an two childs, okay, no problem. And here the only 75 has the children. 25, 125 and 75, they don't have the children. And here you need to remember one thing. The balance factor should be always calculated from the bottom of the tree, not from the top of the tree. Clear everyone? So whatever the nodes don't have the children will be considered first as a 0 values. Why, I'll tell you. See here, for 25, do we have any children over here? No. So it will be calculated as a 0. Then for 65 also, 85, 125 and 175. Hope this is clear for everyone. Now coming towards a 75. As 75 have an equal children, the left and the right children, here, as it is in a left children, it is on a one part, a one, and it is also have the another children at right side, so minus one. What is the balance factor formula? Left should be subtracted from the right. So both have the one one. 1 minus 1 is equal to 0. So what is the balance factor of 75? It is a 0. Coming towards a 50. Okay, now 50 have two right childs. Either it can consider as an a 75 or 65 or a 75 or 85. But it have an, a two children at right side and one children at a left side. So if you have one less than, what people have to consider this left child? Here, whenever we have a child at left side, it will be considered as an a 1. So I have taken 1. Now, at an a right side, the values will be labeled within the children, right? So 1 and 2. Here, how many children are there? 2 children, right? So 1 minus 2 is equal to minus 1. Did you observe or not? Here, till here, whatever the values we people are calculating, the value range is 0, 1 and minus 1 only, not beyond that. So till here, it has been balanced. Now we'll come towards the checking of 150. Coming towards a 150 node, here, you just check it out. The left child is 1 and then a right child is 1. Same as a 75. Here also, left child minus right child is equal to 0. So the 150 balance factor is equal to 0. So here the 50 balance factor is minus 1. Clear now? Okay. Now coming towards an 100. The root node. The root node carries over 100 value. Now these particular node have a children. How many children it has? You can check it out. If you go within a left side, two children. It has two children. If you go within a left with right sides, it has a three children, right? So the highest value, the height of that particular value we need to consider. So I am considering the third one, means 85, 75, 50. Means either you can go with 65, 75 or 50. Either of the thing, the height of the main nodes will be considered. Means Here I have on a left side 3. Coming towards on the right side, I have only 2 children for 100, 150 and 175, or else 150 or 125. So 2. Now 3 minus 2 is equal to how much? 1. So overall balance factor has been calculated for AVL tree. In this way, you need to calculate the balance factor. Hope this is clear for everyone. Now, we'll check it out how the representation will be taken place. The representation is nothing but the whatever we have seen in the diagrammatical part, that is kept in a statement. Here, the AVL tree follows the property of binary search tree with balance factors of -1, 0, and 1. See, -1, zeros, and 1s, not beyond that, the values. Next, coming towards the balance factor is denoted at the right top corner of the node, means here. Right top corner of the node. It is not means here we can't write. That's why. But it is coming towards on the right side. So it will be always denoted at the right top corner of the node. Next, after the insertion of any node in the AVL tree, if the balance factor of any node becomes either -1, 0, or 1, then it is said to be AVL property is violated. Means after calculating all these, if the range is in between, the values balance factors are in between -1, 1, 0, then it is called a perfect AVL. If in any case, if it ranges 2, 3, 4 beyond the 1 or -1, 0, then or else -2, then that is not considered as an AVL 3. Clear everyone? Now coming towards the structure of that particular. Here, as the in the AVL node, we should take the value for the data, means the data of the particular node. Take one node and take the data of that particular node. In that particular node, compulsory we need to have the address of the left tree and address of the right tree. Address in the sense either it is left side or the right side. Address will be giving that information. Clear? Means if the node, the root node has a less value of the child node, then that will be given at left side. That is called the address of the left side. And if the root node has a greater value of the child, then that will be given at the right side. So that is called as a right address of the AVL tree. Clear? And for this AVL tree, the main thing you need to check it out for a balance factor. Okay, so this is the structure of the particular node you need to construct. Struct AVL node in the block, take the data as an integer. Now generate the addresses, whatever the AVL tree required. The AVL tree required the left pointer and then the right pointer. Then check out the balance factor in the form of an integers only, not the imaginary values. Here, this is what the brief introduction of the AVL tree. Now coming towards the rotations. The AVL tree has rotations. Based on the rotations only, the further AVL tree is constructed. Why? Because the binary search tree may have number of levels or the degrees of the particular tree. To balance that one, the rotations will be taken place. Here we will be coming across 4 rotations. Left-right rotation, right rotation, left rotation, and right-left rotation. Clear? So coming from the basic rotations, how the rotations will be taken place in a particular tree. Now we'll check it out with the left rotation first. When a node is added into the right tree, okay, into the right subtree of the right, into the right side of the tree, if the tree gets out of the balance, we do a single rotation. And let me clearly explain you. Here, A is acting as a root node, and B and C are acting as a child nodes. And these are connected at a right side. The left side, there is an empty nodes. Now, to, when you calculate the balance factor, it is unbalanced. So to balance this particular thing, you have to take the rotation. So now I am taking the rotation towards the left side as there are no childs at the left side. Now, these A will be rotated towards the left child, B will be acting as a root node, and C will be acting as a child. So the overall picture will be coming in this way. B will be acting as a root node, A will be acting as a child, and C will be acting as a child. Now, if you consider the balance factor for this, as these two don't have the child, it will be acting as a zero, and we have two children with left and right, then 1 minus 1 is equal to 0. Now it is balanced. It is said as an AVL tree. Clear? Previously it is unbalanced. It is not considered as an AVL tree. In this way, the left rotation will takes place. Now coming towards the right rotation, the vice versa of a left rotation. Here in the right rotation, the values will be added as a child to the left and the child to the left side. Okay. Now there are zero childs at a right side. Now to balance that one, the same thing will be taken place, but in the opposite direction, in the clockwise direction. Right side will be considered. Means these particular root node will be rotated towards the right as an clockwise, and in the left it will be calculated as an anti-clockwise. Have you checked on it? Here left rotation anti-clockwise, in the right rotation clockwise direction. Now the A will be acting as a child for B, and C will be acting as a child for B. Now, if you check the balance factor, now the balance factor is considered. I mean, has been generated properly. Now, this is called as an AVL tree. So, one thing basically you need to remember, if you go for a left rotation, anti-clockwise rotation will be taken place, and if you go for a right rotation, clockwise direction rotation will be taken place. Now coming towards a left-right rotation. Here you need to take two rotations, left rotation as well as a right rotation. Why? Why is there any need? Yes, if we consider the tree in such a way that if a root node has a left child and that child has another child, then that will be considered as on the right side. Now the child is one side at left and one child is at right side for the another child only. Now here we need to take the we need to balance that particular AVL tree. So how we will balancing this particular tree? First left rotation. Left rotation means the A will be rotated towards an anti-clockwise direction. Clear? Got it? Now, we will be acting in between the parent, we will be acting as a parent to the A. Next, again for the right rotation, still it is not balanced. Again, this C will be rotated towards a clockwise direction, towards on the right. Now, B will be acting as a parent, then that will be balanced in this way. At last, the tree is balanced and it is showed as an AVL. Clear? Means A is rotated at a left side and C is rotated at a right side. This is called as a left subtree. Next, coming towards a right-left rotation. In this right-left rotation, here also the combination of two rotations here, but we have to consider first right rotation, then left rotation in the same fashion. Why? Because here A has a right child and that particular right child has another subchild of a left child. These rotations, if you balance, then that will give us an AVL. See here. Now, the to balance that one, first of all, I am rotating the child node C towards on a right side. Okay, the right side means B is becoming as an a parent node and C is becoming as an a child node. Now I am rotating A, the root node towards an a left side anti-clockwise. Now this particular B is becoming root node for A. Now B is an a parent node for A and C. Here the tree has been balanced. Clear? In this way, the rotations will be taken place to balance an unbalanced binary search tree. Coming towards an applications, it is used in huge records in the database for an efficient search. If you go for any database records, if you want to search one record, then this AVL search tree will be helpful to get exact record. And it is also used in memory allocations, just like sets and dictionaries, to search in a particular variable. And this also helpful in database applications where insertions and deletions are less common but frequently used. Now, software needs the optimized search, and it is also used in the corporate offices and storyline games. These are the applications, few applications we come across. Now, coming towards the advantages of AVL tree, as it is a self-balanced AVL tree, it is not surely change the particular positions frequently, and it looks faster than the red black trees, and it is better in searching the time complexity when compared to the binary tree, and the height cannot be exceeded beyond the log n, where n will be the number of nodes in the tree. Coming towards the disadvantages of AVL tree, it is difficult to implement. If the why difficult means, if the balance tree is not balanced correctly, then it is not considered as an AVL tree. So if you take care of that balancing factor, then it is very easy. Otherwise, it is difficult to implement. And it has a high constant factors for some of the operations. And it is less used compared to red black trees. And due to this rather strict balance, AVL trees provides complicated insertions and removal operations as more rotations are performed. When compared to this, why the red black is better than AVL is nothing but here in AVL, number of rotations may takes place to balance the height. But in coming towards a red black tree, you can go for only 2 rotations. This is the drawback, and it takes more processing for balancing. This is what information about an AVL tree. Thank you.